Right, in this session we will discuss the factors which influence the Larmour frequency. Right, here we are discussing the classical approach to the principle of nuclear magnetic spectroscopy. Right, so Larmour frequency, I have already discussed these factors. So Larmour frequency directly depends upon the strength of the magnetic force applied, and so we have already discussed this thing in the quantum approach when we are discussing, right? So if the applied magnetic field strength is 1.41 Tesla, so the nuclear spins with 60 megahertz frequency, and if you go on increasing to 2.35 Tesla, so the spin frequency increases to 100 megahertz. And if you go on further increasing like this, so evidently the spin frequency is increasing, right? So as the force on the nucleus increases, the spinning nature of the nucleus increases, the spinning precision frequency also increases, right? So, and the second factor, it is gyromagnetic ratio, right? Gyromagnetic ratio, it is a natural characteristic of a nucleus, right? So under the influence of gravitational forces, right? So here when you compare proton with carbon 13, right? So proton will have so relatively 4 times higher gyromagnetic ratio, gamma value higher than carbon 13, right? So in a case, if you irradiate or if you influence this proton and carbon 13 with the same external magnetic forces, that is at 1.41 Tesla, as we discussed, this proton precedes with a 60 megahertz frequency, and here at the same time the other nucleus, carbon 13 nucleus, which is having a relatively 4 times less gamma values, and this precedes at 15.2 megahertz. See, so both are experiencing same external magnetic field, but this proton nucleus spinning with a 60 megahertz Larmour frequency, at the same time carbon 13 spinning with a 15.2 megahertz. See, so this Larmour frequency directly depending upon the gamma value. And the third one, magnetic moment. So absolutely the magnetic moment of each nucleus will be different, right? So that depends upon number of protons and number of neutrons, and the combination of protons, how the number of protons and number of neutrons are there, whether that is in even number or odd number, or even combination, even odd combination, or odd combination. So this combination, this number will influence the magnetic moment of the nucleus. Higher, evidently higher the magnetic moment of the nucleus, higher will be its magnetic nature, higher it depend here it will be influenced by the external magnetic field, right? The fourth one is right, electron density around nucleus, right? So here so far we have discussed the nucleus under the influence of external magnetic field, right? So nuclear under the influence of applied magnetic field, right? And what happens if there is electron? In general, naturally you could not find nucleus could not find a nucleus without electron, right? So this is a theoretical case, but in general it is impossible. But naturally all the nucleus, okay, will have some electrons surrounding around it, right, associate with it. So this is the natural case and this is the experimental case we have to deal. And here, so when here in the case of a bare nucleus, only nucleus influencing or experiencing the total the external magnetic field. And here, so when you apply this force on the nucleus, here these electrons spinning, electrons is also charged species, right, with according to magnetic electromagnetic rules, right. So any spinning body which is in the motion, or any charged species which is in the motion, so they create their own magnetic field, right. So this magnetic field created by this spinning or the motion of this electron, which will, okay, which will obstruct the applied magnetic field, right. So this makes this nucleus to experience less magnetic field than expected, right. So if, let us suppose, if 1.41 Tesla we are applying, and here this is the electron which is the charged species in the motion or in the spin around the nucleus, and let us suppose it will this is arbitrary number, right. So this electron motion will create 0.01 Tesla of magnetic field, magnetic movement, right. But this, the direction of this electron magnetic movement is quite opposite to the applied magnetic field. So hence this nucleus, instead of experiencing the total 1.41 Tesla, so now, so due to this electron's motion around this nucleus, it will experience 1.41 minus 0.01 Tesla, right. So means, so the nuclear will experience less external magnetic field strength. So here this nuclear will experience 1.40 Tesla rather than the applied magnetic field, right. So when this nuclear experience less magnetic field, so less magnetic field, so this is the applied and this is experiencing, right, experimental, right. So H experimental is less than, right. So therefore lambda L original is less than lambda L expected, right. So that spinning nucleus will precess with less frequency, right. So it depends upon number of electrons around the nucleus. Higher the number of electrons around the nucleus, higher will be the secondary magnetic field generated by electrons, which opposes the implied primary magnetic field or external magnetic field, right. Higher will be the number of the electrons, higher will be the magnetic force generated around the nucleus, so that will obviously object with the applied magnetic field. So higher and lower will be the magnetic field experienced by the nucleus, lower will be the lambda frequency, Larmour frequency of this nucleus, right. So here let us discuss, and in the applications of this proton NMR we will clearly discuss all these things. So here it is a propyl halide, right. generally chlorine or bromine. So these are highly electronegative when comparatively to carbon and hydrogen, right? So here let us discuss the electron cloud or electron density around these protons alpha, beta and gamma carbon protons, right? So as alpha carbon protons are very nearer to this higher electronegative atom, right? So due to high electronegativity, it will pull the electron density towards this electronegative atom, since this proton will experience more external magnetic field, right? And when you move further from this carbon to this carbon alpha to beta, so the distance increases, so the electron density will not be greatly altered. And if you move further from this higher electronegative atom, so the electron density will not alter a greater, right? So if you compare the Larmour frequency of lambda L1, lambda L2, lambda L3. So lambda L1 is greater than lambda L2. New Larmour frequency lambda L2, new L3. So new L1 is greater than new L2 is greater than new L3, right? So here, so in this molecule, a propyl halide or a propane derivative molecule, this X is higher electronegative atom, which will pulls the electron density from this carbon skeleton, right? So the first carbon, alpha carbon, will experience the more electrons away from this proton. So these protons on alpha carbon will experience more external magnetic field, and they process with a higher Larmour frequency. And when you move further from this alpha to beta, beta to gamma, so the force of these higher electronegative atom are is going to decrease. So here the Larmour frequency also decreases, right? And so the electrons around this proton will not alter greatly, so that electron will influence the external magnetic field, right? So when the electrons influence the external magnetic field, so the nucleus will experience less external magnetic field, so this will process with lesser Larmour frequency than expected, right? Right. There are other factors, that is so this is also a nucleus factor or a symmetrical factor. Nucleus factor, there are few nucleus factors we are discussing: gyromagnetic ratio, magnetic moment of the nucleus, and this is the other nucleus factor which will certainly influence the Larmour frequency or the magnetic field experienced by the nucleus, right? So here there are few molecules, are generally they are unsaturated molecules. So these are the unsaturated molecules which are having pi electron current, pi electron movement between the atoms or the groups, right? So right, so in the case of this, all the unsaturated molecules which are having pi electron current and pi electron movement, right? So pi electron movement will generate the secondary magnetic field. Sometimes the secondary magnetic field generated by these pi electrons movement, right, so may align with the external magnetic field, right? So may align with the external magnetic field, right? So in the case of alkenes are double bonds, so here these the magnetic field generated by the pi electron movement will be aligning with the applied external magnetic field. But here in the case of this acetylene or alkynes, right, acetylene or alkynes, so here in the case of acetylene and acetylene derivatives, so due to this pi electrons movement, so the secondary magnetic field generated in the molecule will associate with the external magnetic field. So hence the total magnetic field experienced by this nucleus, its total will be equal to H applied and H induced. H secondary magnetic field induced due to pi electron movement, right? So the nucleus will experience higher magnetic field than applied magnetic field. So hence the nucleus will freeze process with higher Larmour frequency than expected, right? So both we will experience in the case of this alkenes and in benzenide compounds, right? And in the case of these alkynes, right, so this pi electron moment, so they will orient like this. So these alkynes in presence of external magnetic field, right? So under external magnetic field, this will orient like this, right? So the magnetic field generated due to pi electron current will oppose the external magnetic field, right? So hence the total magnetic force experiencing by the protons or the nucleus falling in this area will be equal to applied magnetic force minus the opposing magnetic force induced or generated due to this pi electron current. So the Larmour frequency of this will be lesser than expected, right? So this is the cases we have to deal. So these are the factor which influence the Larmour frequency. How this pi electron current, the magnetic force generated by this pi electron current will influence the external magnetic field, right? So it depends upon the orientation of that molecule in presence of the external magnetic field. Here these alkenes and benzenes or benzenide compounds orient in this manner, and horizontally, and here due to this alkynes, so as they are orienting in a vertical manner, so their pi electron current, okay, and the magnetic field generated by the pi electron current is quite opposite to, or in opposite direction to the external magnetic field, right? So these are the cases which will influence the external, the Larmour frequency of the nucleus, right? So in the next class we will discuss the important vocabulary in the NMR spectroscopy, right? Let us stop here.